How hard is it to get the humanoid robot Atlas to do some of the things it's recently been doing? Let's forget the flips and all of that. Let's just look at the running. Maybe you can correct me, but there's something about running. I mean, that's not careful at all. That's you're falling forward. You're jumping forward and are falling. So how hard is it to get that right?
Our first humanoid, we needed to deliver natural looking walking. We took a contract from the Army. They wanted a robot that could walk naturally. They wanted to put a suit on the robot and be able to test it in a gas environment. And so they wanted the motion to be natural. And so our goal was a natural looking gait. It was surprisingly hard to get that to work. But we did build an early machine. We called it Petman Prototype. It was the prototype before the Petman robot.
Mm-hmm.
And it had a really nice looking gait where, it would stick the leg out. It would do heel strike first before it rolled onto the toe. So you didn't land with a flat foot. You extended your leg a little bit. But even then, it was hard to get the robot to walk where when you were walking, that it fully extended its leg and essentially landed on an extended leg. And if you watch closely how you walk, you probably land on an extended leg, but then you immediately flex your knee as you start to make that contact. And getting that all to work well took such a long time. In fact, I probably didn't really see the nice natural walking that I expected out of our humanoids until maybe last year. And the team was developing on our newer generation of Atlas, some new techniques for developing a walking control algorithm. And they got that natural looking motion as sort of a byproduct of just a different process they were applying to developing the control. So that probably took 15 years, 10 to 15 years to sort of get that from the Petman prototype was probably in 2008. And what was it, 2022? Last year that I think I saw good walking on Atlas.
If you could just like linger on it, what are some challenges of getting good walking? So is it is this is this partially like a hardware like actuator problem? Is it the control? Is it the artistic element of just observing the whole system operating in different conditions together? I mean, is there some kind of interesting quirks or challenges you can speak to, like the heel strike or all this
Yeah.
kind of
So one of the things that makes this straight leg a challenge is you're sort of up against a singularity, a mathematical singularity, where when your leg is fully extended, it can't go further the other direction, right? You can only move in one direction, and that makes all of the calculations around how to produce torques at that joint or positions makes it more complicated. And so having all of the mathematics so it can deal with these singular configurations is one of many challenges that we face. And I'd say in those earlier days, again, we were working with these really simplified models. So we're trying to boil all the physics of the complex human body into a simpler subsystem that we can more easily describe in mathematics. And sometimes those simpler subsystems don't have all of that complexity of the straight leg built into them. And so what's happened more recently is we're able to apply techniques that let us take the full physics of the robot into account and deal with some of those strange situations like the straight leg.
So is there a fundamental challenge here that it's maybe you can correct me, but is it under actuated? Are you falling?
Underactuated is the right word, right? You can't push the robot in any direction you want to, right? And so that is one of the hard problems of legged locomotion.
And you have to do that for natural movement.
It's not necessarily required for natural movement. It's just required. We don't have a gravity force that you can hook yourself onto to apply an external force in the direction you want at all times, right? The only external forces are being mediated through your feet, and how they get mediated depend on how you place your feet. And you can't just God's hand can't reach down and give and push in any direction you want. So
is there some extra challenge to the fact that Atlas is such a big robot?
There is. The humanoid form is attractive in many ways, but it's also a challenge in many ways. Um, you have this big upper body that has a lot of mass and inertia. And throwing that inertia around increases the complexity of maintaining balance. And as soon as you pick up something heavy in your arms, you've made that problem even harder. And so in the early work in the leg lab and in the early days at the company, we were pursuing these quadruped robots, which had a kind of built-in simplification. You had this big rigid body and then really light legs. So when you swing the legs, the leg motion didn't impact the body motion very much. All the mass and inertia was in the body. But when you have the humanoid, that doesn't work. You have big, heavy legs. You swing the legs. It affects everything else. And so dealing with all of that interaction does make the humanoid a much more complicated platform.
And I also saw that at least recently you've been doing more explicit modeling of the stuff you pick up.
Yeah.
Which is very, really, really interesting. So you have to, model the shape, the weight distribution. I don't know you have to include that as part of the modeling, as part of the planning. Because, okay, so for people who don't know, so Atlas, at least in a recent video, throws a heavy bag, throws a bunch of stuff. So what's involved in picking up a heavy thing, and when that thing is a bunch of different non-standard things. I think it also picked up a barbell, and to be able to throw it in some cases. What are some interesting challenges there?
So we were definitely trying to show that the robot and the techniques we're applying to to Atlas let us deal with heavy things in the world. Because if the robot's going to be useful, it's actually got to move stuff around, and that needs to be significant stuff. That's an appreciable portion of the body weight of the robot. And we also think this differentiates us from the other humanoid robot activities that you're seeing out there. Mostly they're not picking stuff up yet, and not heavy stuff anyway. But just like you or me, you need to anticipate that moment. You're reaching out to pick something up, and as soon as you pick it up, your center of mass is going to shift. And if you're going to, turn in a circle, you have to take that inertia into account. And if you're going to throw a thing, you've got all of that has to be sort of included in the model of what you're trying to do. So the robot needs to have some idea or expectation of what that weight is, and sort of predict, think a couple of seconds ahead. How do I manage my body plus this big heavy thing together to get and still maintain balance, right? And so that's a big change for us, and I think the tools we've built are really allowing that to happen quickly now. Some of those motions that you saw in that most recent video, we were able to create in a matter of days. It used to be that it took 6 months to do anything new, on the robot. And now we're starting to develop the tools that let us do that in a matter of days. And so we think that's really exciting. That means that the ability to create new behaviors for the robot is going to be a quicker process.
So being able to explicitly model new things that it might need to pick up, new types of things.
And, to some degree, you don't want to have to pay too much attention to each specific thing, right? There's sort of a generalization here.
Yeah.
Obviously, when you grab a thing, you have to conform your hand, your end effector, to the surface of that shape. But once it's in your hands, it's probably just the mass and inertia that matter, and the shape may not be as important.
Yeah.
And so, in some ways, you want to pay attention to that detailed shape. In others, you want to generalize it and say, all I really care about is the center of mass of this thing, especially if I'm going to throw it up on that scaffolding.
And it's easier if the body is rigid. What if doesn't it throw like a sandbag type thing?
That tool bag, had loose stuff in it.
Yeah.
So it managed that. There are harder things that we haven't done yet. We could have had a big jointed thing, or I don't know, a bunch of loose wire or rope.
What about carrying another robot? How about that?
Yeah, we haven't done that yet.
Carry spot.
I guess we did a little bit of a little skit around Christmas where we had two spots holding up another spot that was trying to put, a bow on a tree. So I guess we're doing that in a small way.
Okay, that's pretty good. Let me ask the all important question. Do you know how much Atlas can curl? It's a barbell. Have you? I mean, this for us humans, that's really one of the most fundamental questions you could ask another human being. Curl, bench,
It
exercise
probably
wise.
can't curl as much as we can yet, but a metric that I think is interesting
Yeah.
is, another way of looking at that strength is, the box jump. So how high of a box can you jump onto?
Good question.
And Atlas, I don't know the exact height. It was probably a meter high or something like that. It was a pretty tall jump that Atlas was able to manage when we last tried to do this. And I have video of my chief technical officer doing the same jump, and he really struggled, to
Oh,
get
the
up.
human.
But the human getting all the way on top of this
Mm-hmm.
box. But then, Atlas was able to do it. We're now thinking about the next generation of Atlas, and we're probably going to be in the realm of a person can't do it, with the next generation. The robots, the actuators are going to get stronger, where it really is the case that at least some of these joints, some of these motions will be stronger.
And to understand how high it can jump, you probably had to do quite a bit of testing.
Oh yeah, and there's lots of videos of it trying and failing, and that's all. We don't always release those videos, but they're a lot of fun to look at.
So we'll talk a little bit about that. But can you talk to the jumping? Because you talked about the walking. It took a long time, many years to get the walking to be natural. But there's also really natural looking, robust, resilient jumping. How hard is it to do the jumping?
Well, again, this stuff has really evolved rapidly in the last few years. The first time we did a somersault, there was a lot of kind of manual iteration. What is the trajectory? How hard do you throw you? In fact, in these early days, I actually would, when I'd see early experiments that the team was doing, I might make suggestions about how to change the technique. Again, kind of borrowing from my own intuition about how backflips work. But frankly, they don't need that anymore. So in the early days, you had to iterate kind of in almost a manual way, trying to change these trajectories of the arms or the legs to try to get a successful backflip to happen. But more recently, we're running these model predictive control techniques where we're able to, the robot essentially can think in advance for the next second or two about how its motion is going to transpire.
Mm-hmm.
And you can, solve for optimal trajectories to get from A to B. So this is happening in a much more natural way. And we're really seeing an acceleration happen in the development of these behaviors. Again, partly due to these optimization techniques, sometimes learning techniques. So it's hard in that there's a lot of mathematics and behind it, but we're figuring that out.
So you can do model predictive control for. I don't even understand what that looks like when the entire robot is in the air, flying and doing a backflip.
Yeah, well,
But
that's the cool part, right? So the physics, we can calculate physics pretty well using Newton's laws about how it's going to evolve over time, and the road. The sick trick, which was a front somersault with a half twist, is a good example, right? You saw the robot on various versions of that trick. I've seen it land in different configurations, and it still manages to stabilize itself. And so, what this model predictive control means is, again, in real time, the robot is projecting ahead, a second into the future and sort of exploring options. And if I move my arm a little bit more this way, how is that going to affect the outcome? And so it can do these calculations, many of them, and basically solve for, given where I am now, maybe I took off a little bit screwy from how I had planned, I can adjust.
So you're adjusting in the air,
just on the fly. So the model predictive control lets you adjust on the fly. And of course, I think this is what, people adapt as well. When we do it, even a gymnastics trick, we try to set it up so it's as close to the same every time, but we figured out how to do some adjustment on the fly. And now we're starting to figure out that the robots can do this adjustment on the fly as well, using these techniques.
in the air. That's so I mean, it just feels from a robotics perspective just surreal.
Well, that's sort of the you talked about underactuated, right?
Yeah,
So when
that's
you're
really
when you're in the air, there's some things you can't change, right? You
yeah.
can't change the momentum while it's in the air because you can't apply an external force or torque, and so the momentum isn't going to change. So how do you work within the constraint of that fixed momentum to still get from A to B where you want to be?
That's really underactuated. You're in the air. I mean, you become a drone for a brief moment in time. No, you're not even a drone because you can't.
Can't hover.
You can't hover. You can't.
You're gonna impact soon. Be ready.
Yeah. Have you considered like a hover type thing or no? No,
No,
it's too much weight.
no.
I mean, it's just incredible. And just even to have the guts to try a backflip with such a large body, that's wild. But like,
Well,
how?
we definitely broke a few robots trying that. but that's where the build it, break it, fix it, strategy comes in. You gotta be willing to break. And what ends up happening is you end up by breaking the robot repeatedly, you find the weak points. And then you end up redesigning it so it doesn't break so easily next time.
Through the breaking process, you learn a lot, like a lot of lessons, and you keep improving not just how to make the backflip work, but
Yeah.
everything. Just
And
keeps,
how to build the machine better.
yeah.
Yeah.
I mean, is there something about just the guts to come up with an idea of saying, you know what, let's try to make it do a backflip?
Well, I think the courage to do a backflip in the first place and to not worry too much about the ridicule of somebody saying, why the heck are you doing backflips with robots?
Sure.
Because a lot of people have asked that, why are you doing this?
Why go to the moon in this decade and do the other things, JFK? It's not because it's easy, because it's hard.
Yeah, exactly.
Don't ask questions. Okay, so the jumping. I mean, it's just there's a lot of incredible stuff. If we can just rewind a little bit to the DARPA Robotics Challenge in 2015, I think, which was for people who are familiar with the DARPA challenges. It was first with autonomous vehicles, and there's a lot of interesting challenges around that. And the DARPA Robotics Challenge was when humanoid robots were tasked to do all kinds of uh, uh, manipulation, walking,
Driving
driving
a
a
vehicle.
car, all these kinds of challenges with, if I remember correctly, sort of some slight capability to communicate with humans, but the communication was very poor. So basically, it has to be almost entirely autonomous.
It could have periods where the communication was entirely interrupted and the robot had to be able to proceed.
Yeah.
But you could provide some high level guidance to the robot, basically low bandwidth communications
Yeah.
to steer it.
I watched that challenge with kind of tears in my eyes, eating popcorn with
Us
heart.
too.
But I wasn't personally losing, hundreds of thousands, millions of dollars, and many years of incredible hard work by some of the most brilliant roboticists in the world. So that was why that's why the tears came. So anyway, what have you, just looking back to that time, what have you learned from that experience? Maybe if you could describe what it was, sort of the setup for people who haven't seen it.
Well, so there was a contest where a bunch of different robots were asked to do a series of tasks. Some of those that you mentioned: drive a vehicle, get out, open a door, go identify a valve, shut a valve, use a tool to maybe cut a hole in a surface, and then crawl over some stairs and maybe some rough terrain. So the idea was have a general purpose robot that could do lots of different things. Had to be mobility and manipulation, onboard perception. And there was a contest, which DARPA likes at the time was running sort of follow on to the grand challenge, which was let's try to push vehicle autonomy along, right? They encourage people to build autonomous cars. So they're trying to basically push an industry forward.
Mm-hmm.
And we were asked, our role in this was to build a humanoid. At the time, it was our sort of first generation Atlas robot. And we built maybe 10 of them. I don't remember the exact number. And DARPA distributed those to various teams. that sort of won a contest, showed that they could, program these robots and then use them to compete against each other. And then other robots were introduced as well. Some teams built their own robots. Carnegie Mellon, for example, built their own robot. And all these robots competed to see who could sort of get through this maze the fastest. And again, I think the purpose was to kind of push the whole industry forward. We provided the robot and some baseline software, but we didn't actually compete as a participant, where we were trying to drive the robot through this maze. We were just trying to support the other teams. It was humbling because it was really a hard task. And honestly, the tears were because mostly the robots didn't do it. They fell down, repeatedly. It was hard to get through this contest. Some did, and they were rewarded and won. But it was humbling because of just how hard these tasks weren't all that hard. A person could have done it very easily, but it was really hard to get the robots to do it.
Well, the general nature of it, the variety of it,
the variety,
and also that I don't know if the tasks were sort of the task in themselves help us understand what is difficult and what is not. I don't know if that was obvious before the contest was designed. So you kind of try to figure that out. And I think Atlas is really a general robot platform, and it's perhaps not best suited for the specific tasks of that contest. Like for example, probably the hardest task is not the driving of the car, but getting in and out of the car. And Atlas probably is, if you were to design a robot that can get into the car easily and get out easily, you probably would not make Atlas, that particular car.
Yeah, the robot was a little bit big to get in and out of that car, right?
It doesn't fit,
This is the curse of a general purpose robot, that they're not perfect at any one thing, but they might be able to do a wide variety of things. And that is the goal at the end of the day. I think we all want to build general purpose robots that can be used for lots of different activities, but it's hard. And the wisdom in building successful robots up until this point have been, go build a robot for a specific task and it'll do it very well. Mm-hmm. And as long as you control that environment, it'll operate perfectly. But robots need to be able to deal with uncertainty. If they're going to be useful to us in the future, they need to be able to deal with unexpected situations. And that's sort of the goal of a general purpose or multi-purpose robot. And that's just darn hard. And so some of there's these curious little failures. Like I remember a robot, the first time you start to try to push on the world with a robot, mm-hmm. you forget that the world pushes back and will push you over if you're not ready for it. And the robot, reached to grab the door handle. I think it missed the grasp of the door handle, mm-hmm. was expecting that its hand was on the door handle. Mm-hmm. And so when it tried to turn the knob, it just threw itself over. It didn't realize, I had missed the door handle. I was expecting a force back from the door. It wasn't there. And then I lost my balance. So these little simple things that you and I would take totally for granted and deal with, the robots mm-hmm. don't know how to deal with yet. And so you have to start to deal with all of those circumstances.
Well, I think a lot of us experience this in, even when sober, but drunk too. Sort of, you pick up a thing and expect it to be, heavy, and it turns out to be light.
Yeah, and then whoa.
Oh, yeah. And then, so the same, and I'm sure if your depth of perception for whatever reason is screwed up, if you're drunk or some other reason, and then you think you're putting your hand on the table and you miss it. I mean, it's the same kind of situation.
Yeah.
But
which is why you need to be able to predict forward just a little bit. And so that's where this model predictive control stuff comes in. Predict forward what you think's going to happen. And then if that does happen, you're in good shape. If something else happens, you better start predicting again.
So regenerate a plan.
Yeah.
When you don't, I mean, that also requires a very fast feedback loop of updating what your prediction, how it matches to the actual real world.
Yeah, those things have to run pretty quickly.
What's the challenge of running things pretty quickly? 1,000 hertz of acting and sensing quickly?
There's a few different layers of that. You want at the lowest level, you like to run things typically at around 1,000 hertz, which means that, at each joint of the robot, you're measuring position or force and then trying to control your actuator, whether it's a hydraulic or electric motor, trying to control the force coming out of that actuator. And you want to do that really fast, something like 1,000 hertz. And that means you can't have too much calculation going on at that joint. But that's pretty manageable these days and is fairly common. And then there's another layer that you're probably calculating, maybe at 100 hertz, maybe 10 times slower, which is now starting to look at the overall body motion and thinking about the larger physics of the robot. And then there's yet another loop that's probably happening a little bit slower, which is where you start to bring, your perception in, your vision and things like that. And so you need to run all of these loops sort of simultaneously. You do have to manage your computer time so that you can squeeze in all the calculations you need in real time in a very consistent way. And the amount of calculation we can do is increasing as computers get better, which means we can start to do more sophisticated calculations. I can have a more complex model doing my forward prediction. And that might allow me to do even better predictions as I get better and better. And it used to be, again, we had, 10 years ago, we had to have pretty simple models that we were running, at those fast rates because the computers weren't as capable about calculating forward with a sophisticated model. But as computation gets better, we can do more of that.
What about the actual pipeline of software engineering? How easy it is to keep updating Atlas, like do continuous development on it? So how many computers are on there? Is there a nice pipeline?
It's an important part of building a team around it, which means, you need to also have software tools, simulation tools, so we have always made strong use of physics-based simulation tools to do some of this calculation, basically test it in simulation before you put it on the robot. But you also want the same code that you're running in simulation to be the same code you're running on the hardware. And so even getting to the point where it was the same code going from one to the other, we probably didn't really get that working until, several years ago. But that was a bit of a milestone. And so you want to certainly work these pipelines so that you can make it as easy as possible and have a bunch of people working in parallel, especially when we only have, 4 of the Atlas robots, the modern Atlas robots at the company. And, we probably have, 40 developers there all trying to gain access to it. And so you need to share resources and use some of the software pipeline.
Well, that's a really exciting step to be able to run the exact same code in simulation as on the actual robot. How hard is it to do realistic simulation, physics-based simulation of Atlas, such that, the dream is like, if it works in simulation, it works perfectly in reality. How hard is it to sort of keep working on closing that gap?
The root of some of our physics-based simulation tools really started at MIT, and we built some good physics-based modeling tools there. The early days of the company, we were trying to develop those tools as a commercial product. So we continued to develop them. It wasn't a particularly successful commercial product, but we ended up with some nice physics-based simulation tools so that when we started doing legged robotics again, we had a really nice tool to work with. And the things we paid attention to were things that weren't necessarily handled very well in the commercial tools you could buy off the shelf, like interaction with the world, like foot-ground contact. And so trying to model those contact events well in a way that captured the important parts of the interaction was a really important element to get right, and to also do in a way that was computationally feasible and could run fast. Because if your simulation runs too slow, then your developers are sitting around waiting for stuff to run and compile. So it's always about efficient fast operation as well. So that's been a big part of it. I think developing those tools in parallel to the development of the platform and trying to scale them has really been essential, I'd say, to us being able to assemble a team of people that could do this.
Yeah, how to simulate contact, period. So foot ground contact, but sort of for manipulation. Because don't you want to model all kinds of surfaces?
Yeah. So it will be even more complex with manipulation because there's a lot more going on, and you need to capture, I don't know, things slipping and moving, in your hand. It's a level of complexity that I think goes above foot ground contact when you really start doing dextrous manipulation. So there's challenges ahead still.
So how far are we away from me being able to walk with Atlas in the sand along the beach and us both drinking a beer?
Well,
So, out of a can.
Maybe Atlas could spill his beer because he's got nowhere to put it. Atlas could walk on the sand.
So can it?
Yeah. Yeah. I mean, have we really had him out on the beach? We take them outside often, rocks, hills, that sort of thing, even just around our lab in Waltham. We probably haven't been on the sand, but
So soft surfaces.
I don't doubt that we could deal with it. We might have to spend a little bit of time to sort of make that work.